It's my pleasure to introduce the last speaker of the morning session for today, and this is Michael Polyak from Technion in Israel. He's going to talk about invariants of 3D manifolds by counting planar subgraphs.
So it's a pleasure to be here, and I also would like to thank the organizers, for finally really being able to make this conference, because you probably don't or underestimate the amount of bureaucracy here in Mexico, and I myself had some brief encounter with it, and I now can fully appreciate all the obstacles which they had to overcome, to get us all here. So kudos to the organizers. Anyway, so I'm going to talk on something for which transparencies were more or less ready, because I didn't have time to start anything new, which will be then invariants of 3 manifolds by counting planar subgraphs. So it's an attempt actually to start from some complicated theory, which is this quantum Chern-Simons theory, and to move to something simpler. Just instead of looking at 3 manifolds as such, just encode them in some simple combinatorial fashion, and then just explain how these encodings work exactly, and then that it's just a part of a more general picture, which corresponds also not just to 3 manifolds, but also to links embedded in 3 manifolds, or manifolds with certain structure, or not just a closed manifold, but some kind of mapping toroid, or cylinders, rather mapping cylinders, and therefore the mapping class group, etc. And then I'll discuss, as usual, there's a problem that if you encode some complicated object by simple combinatorial data, very often it's non-unique, and what do we do with that? And then actually I'll go for my main motivation, which is just how some complicated invariants of 3 manifolds then can be stated in some simple combinatorial fashion, and whatever. Okay, so how it all started. Wheaton was present on one of the mathematical talks, and that he asked how should we understand geometrically or topologically the Jones polynomial, because for the Jones it's one of the not polynomials which are very simple to define in many different ways, but we absolutely don't understand topology or geometry standing behind it. And Wheaton just said, oh, well, that's obviously, the quantum Chern-Simons theory, and mathematicians said, but there are some path integrals there. So you have to integrate over the space of all connections with some unclear measure. So mathematicians cannot take it as is. But if you use some standard physical technique of Feynman diagrams, then things work, because you can look at a certain term in the expansion and work only with it, and then it kind of makes sense mathematically. And the mathematical output, kind of what you get from physics, is something which is now known as configuration space integrals. And there's already no relation there to any Lie group or Lie algebra. It's kind of purely disembodied version of the Chern-Simons. That has only space kind of integration, and with this we can really work. However, so while it has its own advantages, so in particular it's really powerful. So it contains something which is known as a universal finite type invariance of both knots and 3 manifolds, and all quantum invariance, or something which is vaguely known as quantum invariance, is determined by these. So while quantum invariants are not exactly of this of this perturbative nature, but you can just think about them as power series where each coefficient is of this type. So it is really powerful. However, it's really complicated technically. So what you do is you look at some configuration spaces of endpoints in your 3-manifold, and then you have to take care of situations where several points start to collide together with a certain speed, and then you look at these stratas, because you have to compactify, you have to blow up, and then you have to glue up together many copies of different such spaces, and then there are so-called hidden strata, and you have to deal with them in certain ways, and then there's something which is known as anomaly, etc. So it is really complicated, and even if your theoretical part is done well, so and you can explain how exactly do you compactify, how exactly do you do these zip-subs and cap off and everything, even then it's extremely hard to compute in any non-trivial example. For example, the simplest anomaly, which appears for degree 4 invariant, nobody knows whether it's 0 or not. And people publish papers, about the behavior, good behavior of the anomaly. It satisfies such and such properties, but most probably it's 0, and 0 indeed satisfies all good properties. But we just don't know, right? And even in the lowest degree invariant for 3 manifolds, which is degree 2 invariant, only by now kind of the question of what is it precisely is settled. So 3 groups of people who published more or less simultaneously, didn't publish, they put it in the archive. Reprints, so there was Taubes and Axelrod-Singer and Kuperberg-Thurston, and all 3 of them had different results. Right? So Kuperberg-Thurston said that it's some version of the Casson invariant, and actually they were correct. Taubes said that it's 0, and it took to the seminar about 1 semester to find out where the mistake was. And Axelrod-Singer said, well, it's not exactly 0, but it's rather trivial, and I don't even know where exactly their mistake was. Right? So it's an unpleasant situation when even in the lowest degree you cannot really calculate anything. So results are known for the totally round and not in the standard 3 sphere, for example. This is more or less the only case which we know for sure. So the idea is just to switch to some simple combinatorial counterpart using this perturbative theory just as a motivation. So you just think, how is it built? What are the features? What can we possibly expect? And then you use it purely as a motivation, because a rigorous passage I still, for example, don't really know how to do it now. We'll discuss it maybe later. But the idea is the following. So just think about your 3 manifold in the following way. It's totally trivial almost everywhere, except for a very thin neighborhood of some planar graph. So if the whole manifold, it looks like kind of a totally trivial piece. So if you look at some configuration spaces and then integrate something, there's no interest in doing it in this empty part. You cannot expect there anything new, anything non-trivial. So the only interesting results which you would expect are when your points in the configuration space fall into your graph, kind of basically on this thin neighborhood of the graph, but then you can play with this parameter and squeeze it onto the graph. So then, indeed, that's what you would expect, that everything will, in some sense, concentrate on this graph. And And then configuration space integrals will turn into something discrete and finite. Now, what can it possibly be? Well, there's a question of what is the correct version of the Chern-Simons theory on graphs. I will not discuss it. I don't know yet. I know some pieces how to construct it. I rather know kind of the outcome. So for me, now it's mainly a problem of reverse engineering, how to construct the concrete, the kind of an honest theory on graphs, which would, give me all these sums of subgraphs. But kind of, if you just vaguely hope that something of that sort exists, then you know what to expect here. And this part really works. Okay, so what you would expect is that if your three-manifold is encoded by such a graph, possibly with some weights on vertices or edges on both, then your invariants you would expect as some discrete sums over subgraphs of a certain type. And the types of the graphs over which you have to sum are just really suggested by the theory. The fact that it's Chern-Simons, that there's some cubic potential there, means that all vertices should be trivalent if you just work with three manifolds, or unitrivalent, univalent legs, which you would get for links. So you know an expected outcome, whatever the theory is. And you just use it as a motivation, right? But what you need is, of course, first of all, to explain how do you encode manifolds by a graph. How do you squeeze all the manifolds into some thin tubular neighborhood of some graph, and also preferably also encode links in the same manner, and then of course just to present some explicit formulas for these three manifold invariants, and how do they transform from these perturbative things into these combinatorics. So what is that type of graphs? So I call them chainmail graphs, and I hope the reason will become clear later. But this is just a planar graph which is decorated with integer weights, and the weights are both on vertices. So each vertex is decorated by some integer, which is called the weight of the vertex. And then vertex is balanced if this weight is 0. And you should think about it as some kind of source of, for example, electric current in the vertex, if you wish. Right? So nothing happens there, and it's good and balanced if there's no defect. And the whole graph is balanced if in all vertices these numbers are 0. And there are also weights on edges. So again, just integers. Can be both positive or negative. There's no positivity in any way. These graphs actually, these are quivers, so multiple edges are allowed. Looped edges are allowed. And there are certain rules. So if an edge has a 0 weight, you can just as well remove it. It's of no interest. And then if you have a pair of a pair of edges connecting the same pair of vertices, then you just can redraw it as one edge, but of the total weight, which is the sum of these. Loops, you can just as well erase them. They're allowed, but by kind of the machinery which you have, you see that you can erase them if they really don't play any role in what follows. So these are formally the rules which we have. We just sum weights on both edges and get one U. You erase a 0 weighted one, you erase looped edges. Okay, so it's all very simple. Now instead of explaining how do I come from a manifold to a graph, which is a non-trivial procedure, I will just present you several simple examples of graphs corresponding to such manifolds, so that you will have at least some intuitive feeling of what's going on. So, for example, a 3-sphere is just one vertex, for example, with actually plus or minus 1 weight on it. And S2 times S1 is just 0-weighted vertex. For the Poincare sphere, the simplest encoding which I know is this. For example, just one H. And this is much more complicated creature. It's a 3-dimensional torus. There are some somewhat simpler presentations, but this one is more symmetric. So I used it here. Now, there is indeed a relation between complexity of a manifold, which you can take in any way, for example, Matveev's complexity of 3 manifolds, and the size of the graph. So to simpler manifolds, you assign indeed simpler graphs. Graphs up to Matveev's complexity 8, I think, I more or less know all. They're all quite acceptable.
Can you give an idea how do you get from?
I will. So now let me just explain you to the opposite. How do I go from a graph to a manifold? And then I will explain how to do the opposite. So suppose I'm given such a graph. This graph is planar, so what I will do is I will construct a diagram of a certain framed link. And then there's a standard topological procedure which is called surgery, which means that I kind of cut out certain tori and then reglue them in another way. And in this way you can get any 3 manifold. So the main non-trivial step is just to construct a surgery link. And it's done as follows. So I just a little bit blow up every vertex into a planar circle. Right, and I think about it as a diagram of the unknot. And by the way, I can orient it, right, because everything is planar, so I just use, say, the standard counterclockwise orientation. Now, whenever I have an H, so let me just explain what I do for plus or minus 1 weighted H. It will be simpler. So I just draw a ribbon between 2 such circles, right? So I just blew up these vertices into some small circles, and now whenever I have an edge between them, I kind of along this edge I put a long ribbon, and then I clasp it in the middle, and this clasp can be positive or negative linked, and it depends on the sign of the edge. Right? So, and as I said, if you have a weight, say 2, it means a pair of edges, right? So I just can explain you what do I do in this particular case, right? But basically, if there would be plus 2, it would mean that I link these things twice. Pretty obvious. Okay, so far I used only weights on edges to construct this link. And then I also put a certain integer on every link component, which is called the framing. And it's just done by graph Laplacian. I used it with an opposite sign from the standard Laplacian, just for simplicity. So I just keep the same weights on edges as they were, and I slightly change the weight on the vertex by just instead of taking the weight of the vertex itself, I now take with negative sign all weights of all edges which are adjacent to this vertex, incident to the vertex. Okay, so we get then a link. Right? So here's an example. So I start from this Y-shaped graph, and I get this 4-component link. Each component has its own framing. You see that the framing is not exactly these numbers which were there before, and this is because of this Laplacian thing. Or I could start, say, from this triangular thing and also get a 3-component link in this way, and this H now goes to this pair of Hopf-type link. So, well, these are different presentations for the same Poincare approaches. And then, whenever you have such a link, then you can just use something which is known as surgery. It's a standard topological procedure to get to a manifold. Okay, and it turns out that any three manifold can be encoded by such a graph, which is not very obvious because, you know, the type of surgery link which I got was very special. Every component was trivial. They were linked in some very trivial fashion. However, it is true, there are several proofs which I know of this statement. And what is good is that I can construct this graph just starting from several different encodings of three manifolds. For example, if I'm given a Hilbert decomposition, this is good. And actually, the graph, vertices of a graph correspond to certain sub-words in a word which encodes the whole homeomorphism of the surface. Or I can start from surgery, and then the problem is how to get the surgery link of this particular type, or from plumbing, or from some covers branched along the link, etc. So there's a procedure for that. And what is also nice is that if you don't have just a bare manifold, but a three manifold with some structure, say spin or spin C structure, then it can be encoded in a similar way. So say for a spin C, I have also just to mark a certain subgraph, which is called the characteristic subgraph, and this will give me spin or spin C structure, or a link in a three manifold. And again, instead of just explaining how do I do that, let me just show you these both graphs are pictures of a left trefoil in the sphere. And this basically is the same type of graphs as before, but with one vertex marked. This is the vertex which corresponds to a knot itself. And all other things correspond to these surgery components. And the idea is that you start from a trivial knot, and then you do some surgeries, which do not change the manifold itself. It's still the same sphere, but your trivial knot is transformed into something non-trivial. Okay? So that's how, for example, it works with the trefoil. And while the encoding is not unique, there's a nice set of moves which allow you to pass from one encoding to another. So if you have two graphs corresponding to the same manifold, then there's a certain set of reasonable moves. So the first one is just you split a vertex and you insert two edges here with opposite weights. There's the next one, which is known in capacity or electric networks as a Y delta move. It's quite a famous one, and here it works as well. And it's a particular case of this capacity network moves, actually. And that's the third one, which is of the same form. Now, my problem is that currently I have another bad move about which I'm totally sure that I can get rid of it, and I don't manage so far. But at least there's a finite set. I didn't tell you all the truth. There's another monster. It lives here, and it did not fit. You don't want to know about it. But the funny thing is that these moves, they appear all over the knot theory. So in particular, say, for example, they correspond to just radiometer moves for link diagrams. If I would look at certain, say, moves here, say, then these are just the moves which I drew here. I will not explain what are these balanced median graphs, but this standard thing also, these median graphs for knot diagrams. And they also have their counterpart in Kirby moves. For example, in Kirby move, if you have such a picture here and the central component has a +1 framing, then you can just twist things around it and they will get linked in this fashion, right? And the framings will change, but you can guess that it's related to this picture here. And this picture where the central component is 0 frame, you can just get rid of it again straight, and it has to do with this same move. Right? So so these moves are, in a sense, expected, and it's interesting that they appear in several related places. And by the way, if I think about the mapping class group, this and this will be two different pictures for the braid type relations for generators of the mapping class group. Okay, and this will be something saying that beta inverse equal to 1. So they also have some sense. Okay, so now when we are done with this encoding, so let's think about this discrete analog of these mysterious perturbative Chern-Simons invariants. So let me just consider the simplest case. I will just look at my matrix, this with the of weights right after I move to this Laplacian matrix. So it has a certain determinant, right? So what is the determinant? So first of all, determinant is the simplest thing, right? Which you can recover from a matrix. And since I have a planar graph, almost all information, of course not exactly, I mean there are certain different planar embeddings of this planar graph, but almost all of this information is encoded in the incidence matrix, weight matrix, right? So I should be able to recover from this matrix a lot of information about my manifold. So it turns out that the determinant is exactly the thing which measures you whether your manifold is a rational homology sphere, yes or no. So determinant is 0 exactly if it's not a rational homology sphere. And you know, it's an integer valued matrix, so it's an integer number. So I'm interested in it, and if it's 1, then it's an honest homology sphere, integer homology sphere, or if it's n, then it's n kind of rational homology sphere. Right? So this is the size of the torsion. So now the determinant you can just on your picture see as follows. So it's just what? So what is the determinant of the matrix? You should take one, so the monomial, let's think about one monomial. In the monomial you should take one term in each row and in each column, right? So row and columns correspond to these vertices, right? So it means that I should look kind of, if I think about an element lambda ij as a certain edge which connects ith and jth vertices, then this element which stands on the ith jth place, it's just an edge, right? And if I require something to have exactly one element in each row and in each column, then it means that there's one edge entering every vertex and then exiting the same vertex, right? So it's just a collection of cycles. And possibly, you know, if I have something on the diagonal, then it possibly kind of the looped edge which starts and ends in the same vertex, right? And the weight, it's just this monomial and the determinant, and it's just you take the product of all these weights of all edges which enter there, you take it with the correct sign. Okay, so if you just count these collections of loops, you know, passing all vertices, then it gives you this determinant, which, as we said, tells you something about the homology of this manifold, and we'll just go on and jazz it up a little. So, so what we expect is, again, count some subgraphs, just like as we counted these collections of loops. And the idea is that instead of configurations of endpoints in your manifold, you look at just the case when all these endpoints settle in vertices of your graph. And edges, propagators, they correspond just to some paths of edges inside your graph. So things boil down to the summation of subgraphs of certain type. And yes, we have something which remains of these problems of compactifications and blow-ups and anomalies, but now they become very simple. It's just some degenerate graphs where several vertices of this graph just come together. It's much simpler to take care of than before. So let me just illustrate it on this example of the Feynman graph with two vertices, which is supposed to give me the simplest non-trivial invariant with three manifolds. This theta graph. Now it has some labels. I just label the edges and I label also the vertices. And I will look at embeddings of these labeled graph into my big graph, which encodes the three manifolds, right? So, and I would count all these embeddings with some weights. Now, how do I do it? So, first of all, I should drop these two vertices into vertices of my graph G, right? So, I should pick up a pair of vertices. I don't know whether you can see them. These two are picked now, they're blue, okay? And then the collection of edges should go into collection three kind of paths of edges which only have common endpoints, right? And then I counted with the following weight. So first of all, I just look at the product over all edges which enter here, right? But my collection maybe does not cover all vertices. For all vertices which are not in the image of this map, I take it the product, the determinant of the remaining kind of matrix, right? Linking them. Anyway, so, and degeneracies about which I was talking about, they now boil down to some simple things, like if I would just, if two vertices of a theta graph would collide, I would get a figure 8 graph. And yes, these I should count also with some reasonable, again, weights. And here's an example of one of the most degenerate graphs where this is, first of all, it's already figure 8, which is a degenerate case of a theta. And also one of the lobes went into a little looped edge here. Right? And then there's a reasonable, kind of obvious way to assign a weight to such an embedding. And the claim is that this is indeed, so if I sum over all such maps, so over all such theta subgraphs, and I count them with correct weights, then it is an invariant of the manifold, and up to a certain normalization, which is 12, H1, blah, 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 and the signature I should explain. So it's a four-dimensional thing, right? My manifold is actually, since I work with surgery, it's a boundary of something four-dimensional. So if you wish, this is the signature of this four-dimensional manifold, or if you wish, the signature is just the signature of this matrix. So, and indeed it's just the Kasson-Walker invariant, or rather it's this extension to all manifolds. Right? Okay, now, so the problem is that I cannot calculate these guys in a sense that I cannot prove so far that they're invariant. I can calculate them and see that they're invariant if I count them correctly. But unfortunately, as I said, in addition to these three moves, which are supposed to work for this non-uniqueness, to take care of the non-uniqueness of the graph, there's this other monstrous move, and I cannot just check it invariant summaries, obviously. So I'm stuck here, but things supposed to work. At least I hope to overcome this. And the nice thing is also that this theta, it was what? It's just some summation over some subgraph. So it's, if I think about it in the entries of this Laplacian matrix, then this is just a polynomial. And it's a polynomial of degree 1 higher than the determinant. So actually a nice polynomial, and several people in the matrix theory, they've never seen this polynomial, but they have really nice properties. And the conjecture is that all finite invariants, I don't know whether I'll have time to talk about that. I honestly polynomials in this, whatever. Now, okay, remarks, example, how do I do it with the Poincare homology sphere? I will not enter it, but indeed I count these things, and you see the count, and it's 24. Oh, and it's again up to normalization. It should be this standard thing about the Kasson-Walker of the Poincare homologies. Oh, good. So, so the nice thing is pulling.
Yeah.
1 more minute. Okay. 1 minute. So, so this mysterious other approach to this perturbative churn silence invariance, coined by probably Cook, Waffa a long time ago, which mathematicians don't exactly understand. And there's some combinatorial version also of this kind of duality, again, about which I will not have time to talk. And the same thing, which I calculated there by embeddings of these theta graphs, I can calculate in a different way using this Laplacian matrix. And in this way, I get the generalization of the classical matrix tree theorem, right, which says that the determinant can be calculated using this Laplacian thing, just as the sum over all spanning trees, or rather spanning forests. So in the same way, instead of counting these theta subgraphs, I can count them with another set of weights, and there I would just, instead of these thetas, count cycle-rooted trees. So instead of the usual trees, which correspond to determinant, so a collection of loops, a theta thing goes into these cycle-rooted trees, and the cycle-rooted trees has an interesting interpretation. Let me just skip it. That they correspond to some, so can be explained in some terms of something which is known as discrete vector fields on graphs. Discrete vector fields are just the following thing, that in each vertex you should have no more than one outgoing edge. So you orient all edges in such way that, not all, but partial orientations of edges, so that at each vertex there's no more than one outgoing edge. So you see that several may be incoming, but say here there are no outgoing, and here there's this oriented cycle, right? So from all these guys, there's exactly one oriented edge. So for these discrete vector fields, there are critical vertices, and these are the ones from which nothing flows out, and there are these closed orbits, and these are exactly the cycle-rooted trees. So in this sense, the determinant or the classical matrix tree theorem tells you that, say in this case, in this interpretation, that the homology of my three manifold I can calculate by counting critical vertices of such vector field. And here I look at closed orbits. So I really count these cycle-rooted trees. Okay, probably let me just stop here. Oh, yeah. Okay. Just stop
here. Questions?
And you detect from the planar graph, weighted planar graph, with three manifolds simply connected? Can you prove Poincare conjecture using your graphs?
I don't think so. No, it's mostly, it's like with the Cousin invariant. He invented it. As far as I understand, the motivation was exactly for the Poincare conjecture. But then it turned out that you can just define it using the fundamental group, right? So there was no hope for this. So I expect that no. And
for the glory of topology, a topological proof of the Poincare conjecture would be very nice.
That would be nice, yes, once in a time. But so far I'm happy that I don't have it messing me up these things. Because that would be a bite which is too big for me to swallow for sure. So, but I don't know. So kind of my next probably step would be to work with manifolds with some structure. So hope to have the same thing fully developed for manifolds with spin C structure, and then to see what else can I do there further. But not for bare manifolds. I don't think so.
Any other question?
I have a But since work on Kroheimer and Morofka, they're doing the opposite. So they're trying to prove like this full color theorem, planar graph, using this Chern-Simons.
Yeah, I mean, you know, everybody, yeah, that's true, but kind of, you know, you have your favorite hammer, right, you, kind of, which you like, and then you look for problems which you can hit, right, I mean, is this nail from this wall, kind of, you know, can I hammer it in? So when you have your favorite technique, you know, then you're looking, so I always like to take complicated things as a motivation, and I don't know how to make things rigorous there, you know, because it's really too complicated. And then, but then you pass to the simple combinatorics, and there you can really kind of, you know, calculate things very explicitly.
Well,
So you have these tables of, you know, this Kasson-Walker for the.
My point is opposite. So the graphs are actually complicated. And I think that they're more complicated than the three manifolds, maybe.
No, well, if you, these are planar graphs. Planar graphs are much simpler than all graphs. That's actually a crucial point. For general graphs, these formulas do not work. That's much more interesting and non-trivial game if I start from a graph which is non-planar, which I also can do, but here this is a very simple class of graphs.
So when you're saying you want to look at other structures, I guess you might consider contact structures and getting Legendre links.
Yeah,
That would be
that's
nice.
kind of where historically I come from. Yes, so, yes, of course. Yeah.
Any other question? Let's thank our speaker.